Hi everyone, and welcome to another episode of Mr. Carlson's Lab. Today we're going to take a look at possibly one of the finest or one of the best vacuum tube voltmeters ever created, and we're going to restore this and make it perform the way it did when it was brand new. So let's get started. This is the HP 410B Hewlett-Packard vacuum tube voltmeter, and as you can see, it's in really nice condition. It has the usual scratches and nicks for something of its age, but all in all, it looks to be pretty nice looking still. As you can see, it has the old handle on the top. Now, a word of advice, if you find something like this at an auction or flea market, avoid the temptation to grab the handle and pick it up, because much of the time these things break right off, and you know what's going to happen? This is going to fall right to the floor right in front of you, and then it's just going to be destroyed. I've seen this happen at swap meets. So whenever you find something old like this, don't grab it by the handle. Always pick it up by the case, just to be safe. It came with the probes, which is nice. So this is just a little connector that screws onto the bottom here and attaches the probes into the unit. You can remove this and all of the probes, as you see here. So this one is the AC probe. It has a vacuum tube inside it. This one here is the DC probe. This is the ohms probe, and then there's a common or ground clip right here. So there's 4 wires that come out of this, and as you can see, they're listed right here. So ohms is the red wire, and as you can see, you could follow AC. You can follow this lead to the appropriate probe, and then DC, you'd follow this to the appropriate probe, which ends up here, and then the common, which is right here. Now, you can remove this and put this in the back of the unit for storage, or if you're going to take this, on the road with you. But most of the time, I find that these things sit on the bench all the time. So it's a good idea, once you put this on, just leave it on. You don't want to put that extra time on the unit by taking this off and putting it on and taking it off. It's just hard on connections and everything like that. So I find that I leave them all connected. On the back side, you can see the line cord coming out of the back. You can store the probes in the back if needed, down in here with the line cord. It's a little bit tight, but everything fits in there. So all the usual adjustments that you need to calibrate the unit. You see a tube right here, and they've listed the tubes right here on the outside, so they're behind this. So Hewlett-Packard made this relatively easy to service, which is very, very nice. So there are a lot of perks about this VTVM, aside being, very, very accurate. Or I should say aside from being very, very accurate. So great meter to own. If you ever have the chance to own an HP 410B, I would say jump on it. If you need a VTVM, this is the thing to have. Now you might be saying, well, isn't a digital meter just as good as a vacuum tube voltmeter like this? Absolutely not. So I've recently posted a video on Patreon talking about how this meter differs from a modern meter, and I show that where a standard DMM, would, even like this test equipment over here, a regular DMM, bench style DMM, will load circuitry. So it'll actually drag the voltage right off of an AGC line, whereas this thing, it's invisible to the circuit. So the input is such a high resistance or impedance, if you like, that this thing here will, it remains invisible to most circuitry. So I'll explain that once I get this thing running, and maybe I'll even include a small little clip of that video just giving you an example of how important this is when you're working on very high impedance or high resistance circuitry, depending on whether it's an AC or a DC circuit, right? So anyways, I'll get this thing out of the case, we'll take a look inside, and we'll get moving with the restoration. Let's make this thing perform the way it did when it rolled off the line. Getting the HP 410B apart is really quite easy. So the first thing that we're going to want to do to service this is get rid of the probes. So we'll remove this and remove this here. Now usually the screws have got little stoppers on the top to stop them from coming out. So I just go back and forth because a lot of the times they unwind. And there they are. So that stops the screws from coming out. You'll find a lot of the times these things will unwind. Looks like this one has come off just a little bit, but at any rate, that removes the entire probe assembly. Isn't that nice? So you can get this thing right out of the way. Get rid of all of these cables just like that. So I'll just put this over here. And the next thing is back, you just press this down, get this off of here like so. Now, of course, this is going to have to stay on the line cord because the plug won't fit through that hole, but not a big deal. See these two screws right here? Remove those and we are in, just like that. Very easy to get inside this. So I'll remove this here. That one and this one here. Everything in real time, right? So there we go. And I'll give myself a little bit of cord because I'm going to lift this up. Look at that. And it looks like it's in really nice condition. It has the antique dust included. Look at that. Everything is there. That's a good sign. And I don't see any exploded electrolytic capacitor, so that's pretty good. Right here, that's looking really nice. This capacitor is looking like it's in fairly nice condition, so nothing really bad has happened at any rate. The rectifier's on the bottom. And that looks like that's okay as well. So our switches here, and lots of resistors to check. And calibration points and everything. So that's what we're going to do next. That's what I'll end up doing is I'll get this thing all set up. I'll move the camera so we can take a closer look at things, and we'll start checking some of the components together. Here's a closer look inside the HP410B, and as you can see, there's a nice row of resistors here to test. Now here's a little trick with vacuum tube circuitry. Vacuum tubes are relatively high impedance devices, and when they're off, they basically look like an open circuit. So it's very easy to test most resistors in vacuum tube circuitry right in the circuit. Now there is the odd case where a resistor will be paralleled with something. You'll have to lift one end of the resistor to accurately check it. But in most cases, you can just go and test most resistors right there. So for example, I'll just choose one. This area has been hot here. You can see it's kind of discolored. So let's test this 10K carbon composition resistor right here. 10.8K. It's a little out of focus because the focus is up here. I should move that over to the meter there. So 10.8K, that's going to be most likely okay. 7.4, so this is a 6.8K resistor, and it's gone up to 7.4. So depending on where in the circuitry this particular resistor is, that may not matter. So if you understand the circuitry that basically surrounds the vacuum tubes, that might cause just a very slight change in voltage from, say, what it originally was measured at, and it a lot of the times won't affect the circuitry. Again, it just depends where it is in the circuitry. So as I go along and explain other vacuum tube circuits here, I'll talk a lot more about that, how to understand if the values really need to be that accurate. A lot of the times in this old vacuum tube gear, they didn't even have a fourth band, which means that they were 20% tolerance. All right. So if this isn't a portion of the circuit that needs to be, relatively accurate, I will replace this resistor, but I'll take some measurements because these are all aged and chances are they're not going to move very much now. If they are okay, I'll just leave them in. Now you'll see that there are some with gold bands here, and I would expect these to be very accurate, and these are most likely in a portion of the circuit where the accuracy really matters. Since this is discolored here, this is probably just, maybe in the power supply portion. Well, you can almost see it right here. There's the capacitor, and, this is most likely part of the power supply. So that little bit of difference is really not going to make a whole lot in vacuum tube circuitry. Now, I know that may sound a little bit contrary to what a lot of people believe because people are used to solid state stuff. And in a solid state circuit where you're dealing with low impedance devices, yes, small changes in resistance values do mean quite a bit. We're dealing with vacuum tubes here, different story. Again, I will go over more of this and how to recognize this and go, oh, okay, this is 6.8K, but 7.4 is absolutely fine. I'll just leave it. I'll explain all of that in many of my future videos. So let's see what else can we test here. So this hasn't been hot. It doesn't look like this 2.2K resistor. Let's just test it. So you can see it's kind of darkened over here. So these have gotten warm. So let's test the 2.2K and see what it says. No problems. 2.1K actually. And as you can see how it's slowly climbing, it went down and now it's slowly climbing up. That usually indicates that there's a capacitor somewhere in circuit. So no problems. So look at this, 3.9 megohms. Let's see what that is going to do. Not bad. So most of the resistors here are most likely going to be okay. Again, I will look in the circuit, find out where these things are, and if they need changing, they'll get changed. I have lots of carbon composition resistors. So over here, we have two 12AU7s, which are dual triodes. Over here, we have a ballast tube. And this ballast tube is used for the probe. So they have this in line with the filament of the actual tube inside the probe to act as a form of regulation. Here's another regulator tube. This one here, I'll just get the focus on that right there. This here is a regulator tube for the B+. So the 6X4 will be the high voltage rectifier. This will be a regulator circuit to make that nice and stable. And down here we have a very nice looking rectifier. Look at that. What a nice color. And it looks like it's in pristine condition. Here are all the resistors that make this thing very accurate. So what you're reading with your probe equals what you're seeing on the meter face. And yeah, just it's pretty standard. Surprisingly simple design is what I would say for something that is so incredibly useful. Honestly, these are just wonderful, vacuum tube voltmeters. So what I'm going to do now is I'm going to just go through and test all the other resistors, and this capacitor is going to get changed. It's a really low value. I believe it's like 4 microfarad or something like that. Yeah, 4 microfarad at 450 volts DC. So I'll end up testing this too as well, just for the fun of it, to see what condition that is in. And we'll pretty much power the thing up and see if the thing works. There really isn't a whole lot to this. There isn't a whole lot to a restoration like this. So if you're interested in getting into vacuum tube equipment restorations, this is a very, very simple restoration to start off with. Of course, know that all of these devices have high voltage inside them, right? Because vacuum tubes work with elevated voltages. So if you're unfamiliar with working on a device like this that has high voltage in it, don't do it, right? Do your research. And when you feel that you're qualified to do so then. So if you're following along, you're definitely doing so at your own risk. Just be very, very careful. All right, I'll get some components changed and we'll turn the thing on and see how it works. And I'll show you some of the bad components as well that I find. All right, let's test this capacitor here and see how well it tests out still. May be good, may not be. So judging by the condition of this thing, it looks like it is rather low time, but depending on the facility or wherever this thing was used, there's a really good chance that they just took really good care of it. So what I did is I just cut there's a small ears that I call them. What they are is they take the wire, put it through and fold it over, and it makes what looks like an ear. And what you do is you just clip those little loops off, and it'll allow you to very easily desolder something like this. So what I'm going to do is I'm just going to position it like this, so I can see the wires from my angle. And what I'll do is I'll just heat this up like so. And as you can see, they just come right out. So I'll just move that out of the way, move that out of the way. And let's test this for capacitance. So let's see if I can get this all in here. Turn this on. So it should be around 4 microfarad, something like that. So the ground of this looks to be isolated from the chassis, because they've got the 2 wires coming to the ground here of the capacitor, and then they have an insulating, you can see that, this little insulating wafer here. So something to keep in mind if you're going to try and replace something like this. A lot of them have those little tabs that twist or bend out. In this case, the capacitor's negative is isolated from the chassis. Okay, so let's see if this will tell me anything. All right. Oh, 9. So you can definitely tell that it's a real overachiever of a capacitor. Or it's definitely, on its way out for sure. So let's see. A lot of these older capacitors were overachievers. Just the way they were. So what I'll do is I'll grab the other tester here. This is a leakage tester. And what this is going to determine is whether this is electrically leaky inside, so whether this is beginning to look more like a resistor than a capacitor. So one of the big tricks, or one of the clues that these things are getting leaky, is this was rated at 4 microfarad, and we saw this capacitor tester indicating about 9 or over 9 microfarad. Well, why is that? Well, these capacitor testers use math to determine what the capacitance of the capacitor is. So what it's doing is it's measuring the amount of time it's taking to charge this capacitor and then converting it into a number here in microfarad. So what's going to cause this to read higher? Well, if you add a resistor across this, it's going to take longer for this to charge. So we would put a resistor in parallel with a capacitor. You would take this longer to charge up, and then this is going to indicate a higher capacitance. So that right there is a clue that this thing is going to be leaky. All right. So to really determine that, we use a dedicated leakage tester. So what I'll do is I will put this on here. This is one of the little devices I've designed, and this is available on Patreon with all the plans and everything. So if you want to build one of these things for yourself, it's all up there. Schematics, alignment procedure, plans, the whole, everything, whole ball of wax. So you've probably heard of ESR, equivalent series resistance, right? This is testing for parallel resistance. So completely different test than an ESR tester. All right. So I'll move the focus over here so that we can see it a little bit better. So what I'll do, this is on the electrolytic position right now, and I'll put this, that's discharge right there, and this is test. Already I can tell that this is very leaky. It's still in the red scale. Yeah, very leaky. Okay. So what I'll do is I'll shut this off. Now, this is reading roughly 9 or 10 microfarad. So I have a 10 microfarad capacitor. Let's compare it to a really good capacitor. All right. So if this is 4 microfarad, and this is 10 microfarad. So say this was 4, right? It was actually reading at 4. This should take twice as long to charge. So you'd see this move down a lot slower than this one right here. All right. This is a newer cap, so let's check it out. Okay. So let's put that onto the side here, like so, or here where we can see it. And put onto discharge, and here we go. Look at how good that is, just zipped right through that second scale. So no problems with the new cap. So you can see how bad this is, right? You see how quickly that moved down the scale. And this is why you avoid the temptation to plug these things in when you first get them and just to see if they work. Because a lot of the times these capacitors are turning into resistors. And when they turn into resistors, they put extra load on the B+ section in the unit itself. And when that happens, it damages components. The most common thing to happen is these things will go closed completely, they boil, or they'll blow the cathode bonding wire off the rectifier tube. So you definitely want to avoid that temptation. So very useful piece of equipment to have on the bench, and it's low voltage as well. So this unit here is much safer to use than the older capacitor testers that use high voltages to test caps. Again, available on Patreon if you want to build one for yourself. Definitely check it out. So what I'll do now is I will install this, because I'm going to replace this 4 microfarad with 10 anyways. A little bit of extra filtering won't hurt anything. So I'll add that in here and on to the next portion of the project. I've installed the new capacitor right here. So they're so small now they pretty much fit anywhere. That allows me to leave the original capacitor in and maintain that original look right over here. So what I've done is I've disconnected the wires from the original positive lug of the capacitor, and I've installed a little standoff. This is a ceramic insulator right here. And I've just moved the wires from the lug up to this insulated area right here, and I've put the new capacitor across this. So this allows me to very easily change a capacitor down the road if I need to do that. If I was to restuff the can and do all that, you know, it's quite a bit more maintenance to get in here. Now this thing is not going to be a shelf queen. I'm going to end up using this thing all the time. So this is a piece of equipment that I, plan to have on the bench and use and, you know, display its functionality. So the new capacitor worked out well, and now what I'm going to do is start cleaning all of the switches down here, and I'm going to get it ready just to test the thing out. Let's see how it works with all of the original resistors in here. All right, let's try this thing out. Let's give it a shot and see what it does. So we'll have to wait a few moments here for this to warm up. So I have my power supply set to 1 volt. And it's on the 1 volt scale here, so I'll have to wait for things to stabilize here. I've left the selenium rectifier in just because it's fine. And not only that, there's hardly any load across it. It's not really in a high voltage application, so it should be absolutely fine to be left alone. Now, if this was in a B+ application, that blue selenium, I'll show you that here in a little bit again, I would end up replacing that with a diode. But again, low current, not a big deal. It should last the term. Okay. I'll just zero this off. So what I'm going to do is I'm going to take the DC probe and I'm going to short it to ground here. And I will zero this up. Should be close enough for now. Okay, let's see what it does at 1 volt. Pretty close. 0.9, a little bit under 0.9 of a volt. Now keep in mind this is also sitting on its back and I haven't zeroed the movement out. So these meters, they like to sit straight up and down. So not bad, really, without anything really done. So not too bad at all. So let's see. You can see it sits up a little bit here. And I take the probe off. You can see how sensitive that is. It moves all over the place. Just me moving my hand around it is just very, very, very sensitive meter. So let's try a resistor. Okay, so this should be fun. Go to ohms. Move this from the power supply, and I have to use the red probe now, which is wrapped around everything on the bench. So get that one out of the way, and these are the two now. So what I want to do is I want to adjust this for infinity, right? So it's basically the last line. You can see the infinity symbol, the last line right there. So I'll bring that up. And then what I'm going to do is short these, like so, and then I have to zero this out. And you have to go back and forth a few times with these things, sometimes. So this is on the lowest scale too, so it's going to be real picky. So I'll open this up. And now we need to adjust this for infinity again, or the last line. And I'll short this again. And adjust for 0. Again, I am on the low ohm scale, so this is a really picky adjustment. And I'll open this up again. And I'll adjust that right up there. Short this. Like so. Oh, it's getting close. Just bump that up to 0. Alright, let that stabilize one more time. And I'm just about there. Look at that. Just about there. Just a touch. I want to get this about as accurate as possible so we can get a really good idea of how well this thing's working. Okay, not bad. So I'll rummage around over here. I think I have a lower ohms resistor here somewhere. I do. I think this is a 3.9. Yeah, 3R9. So this should be 3.9 ohms. Okay, so let's see. Should be right around the 4 if this is accurate. Let's see what happens. Are we still on that line? We are. Look at that. No problems there. No problems at all. So let's see. What else should we try here? Let's go to the next scale here. I have a 220 ohm resistor sitting off to the side. Now you can see how different this is. So again, I'll adjust for an infinity. Move this here. Now I haven't tested any of the tubes. These meters are very sensitive with the 12AU7s. So if you can match the triodes in a 12AU7, it's the best thing for these meters. So I'm going to design a tube matcher for triodes, and I will release that on Patreon. So anyways, just another thing planned. Okay, so let's short these out and go here, zero this again. And then I'll open the probes and bring this to infinity. And then short them. Getting close. Make sure there's good connection there. Very, very close. I'm getting kind of picky now. Let's see if it goes to infinity. Okay, so 220 ohms. Here we go. Attach this. And here. Look at that. It's right on the line. So it's 220, 240, 260, 280, 300. So that's 220, that line right there. Okay, I'll zoom on in. Make things a little bit easier to see. Look at that. It's pretty good. Not bad. No alignment yet. So nothing has happened with this thing. As I said, pretty nice meters. All right. Now what I'm going to do is test some of the tubes in here, and if I find a weak one, I'll let you know, and we'll proceed and move on and try and do a 1 volt calibration. Doing the 1 volt, here, I'll just back this out because you can't see what I'm pointing at. Doing the 1 volt DC calibration calibrates the entire DC scale. The AC scale needs to be calibrated by multiple variable resistors inside. So far the ohms is spot on, and the DC is not far off. So what I'm going to do is test the tubes and I'll be back. All right, I tested the tubes and I put them back in so I can show you what I'm about to do here. So this tube right here has seen better days. So what I'm going to do is just remove the retainer like so and replace this one here. So this one here didn't test very good at all. So I was looking through my pile of stuff and look what I came across. Hewlett Packard, and it tests wonderful, 12AU7. So I will put in the Hewlett Packard tube into the Hewlett Packard meter. Just by doing that, this should magically work, right? Okay, so now let's turn this back this way. And I'll put these under here to steady things. It's right at the top. So let's see if we can get any closer. Right now, put this back into my isolation transformer, current limited variac supply. Turn this on. I'll attach this to my DC supply. We're still set at 1 volt. And I'll let everything settle off here. Things need to warm up. This probe over here. And I'll short this here. You can see how far off this is, right? So I'll just move this up. If you recall, when I was zeroing the meter for DC, it was almost right over to the stop. Now this is way up, almost centered, actually. Okay, so I'll just bring that to 0. We're on positive DC volts, and it is 1 volt again. Now keep in mind this isn't warm, so let's try this out. Oh no, we're on the wrong scale. I'm on the 3 volt scale here. I'll do that again. I'll zero that up. Still from the testing the resistor. I didn't move that back. Okay, so here we are. There you go. So you know that there's no pre-testing before I do this. It was still on the scale I was using for resistance loss. Okay, so here we go. And I've zeroed it up. And as you can see, again, there's lots of room. It's pretty much centered, right? So I'll zero that there. Okay. 1 volt. Let's see what happens. Look at that. So now it's a little over, so it could use a touch on the cal there. So again, I'll short this out, make sure everything's zeroed properly. Yep. And right there. No problem. So I wonder if I stand this straight up, if it'll just read right on. Wouldn't that be something? Again, meter movement, right? I don't know if you can't really see this, so I'll move this out of the way, move this back here. Maybe you can. Well, you'll get a slight view of it anyways. Let's see if I can prop this up on something. I think this may hold it. Okay. A little bit unsteady there. Put this one under this side. And it won't go crash bang. Alright, so there we are. Let's see if I can zero this up. Grab that DC probe again. That's one of the things that's tricky. You end up grabbing the wrong probe all the time. So I'll zero this up. And it's pretty much zeroed still. So I will give this 1 volt. And yeah, it's still a little bit over, so not bad. On the from this angle, it looks like it's way over, but looking at it straight on, it's half a bar over the 1. So not too bad. So if I adjust this here, maybe if I lay it down, the DC cal will be right here. Why do I know this? Well, I have worked on many of these meters. So here we go. So I'll just adjust that down to sit right on the 1. So it's sitting right on the 1 right there. If I short this out, it's right on the 0. Okay, so let's see if it reads the same now when this is sitting back like it was before. That would be nice if it does. Okay, so here we go. So I'll short this out. Just about. Oops. Really trying to bury this probe into that ground there to get the most accurate 0 I can. Let's do this. Very close. Okay. Let's try it now. 1 volt. Look at that. Right on 1. So let's try, for the fun of it, 0.6 of a volt, which would be right there. Alright, 0.6. 0.6. Enter. Okay, let's see what that does. See what I mean by fantastic? So far, so good. The roughest calibration you've ever seen on the bench, meter laying backwards, everything still performing good. So that weak tube was definitely part of the issue. So, and of course now that it has a Hewlett-Packard tube in there, it feels right at home. All right, so what I'm going to do is I'm going to clean the rest of the adjustment VRs here. So I'll just shut this off and remove this from my isolation transformer and current limited variac supply. Grab the frame here. So what I'm going to do is I'm going to just spray cleaner in all of these and move them around a whole bunch of times, and then get this ready for a real calibration. You know, get the dust off of this and everything. You know, it's still pretty filthy in here, right? And again, I was going to tell you about this. I tested this down here. It's absolutely fine, right? Because the selenium rectifiers or any type of rectifier should be tested, just because you don't know what's, you know, happened over the years. I just tacked this back on just in case I was going to, you know, fit another diode in there, but it's absolutely fine. There's no problems with it. And it's in, again, you know, a low voltage portion of the circuit. So, and no, not very much current demand on it or anything like that. So I'd like to leave it in. So, you know, that's personal preference. If you're scared of those types of rectifiers and you want to change them, you know, feel absolutely free to do that. All right, I'll clean some VRs. Let's perform an alignment here, and we'll also try out the AC probe as well, right? Because we need to do a complete AC alignment. The tube in the AC probe is working very well. Here, I'll just show you something. I'll show you the tube inside the probe. It's very easy to change. There's 2 different types of tubes. There's an EA53, which is the 6.3 volt version, and there's a, what is it, 02, I think? 2-01, 2-01C, I think. So when you take this apart, be careful that you don't lose this, because there's a little spring-loaded tip on here, and that makes connection inside the top there. You see that right at the top? So you don't want to lose those. This is a little vacuum tube right here, and it just plugs in, like so. So this one is the EA53. So the EA53 is the 6.3 volt version, and the other one is the 5 volt version. So I'll just put this on here. So it just depends which tube you have. Put that back on. So if you have the 2-01C, it may require a little bit different alignment for the filament voltage. Just put that on like so. And wind that back on. So for higher frequency use, if you're going to be testing, you know, around the gigahertz range or something like that, of course you'd want the shortest leads possible, and they have this clip on here that'll allow you to, you know, have a pretty short lead. At 1 gigahertz, this is still, you know, quite the inductor. But, you know, you would want a very, very short ground. And of course, you know, even at 1 gigahertz, this amount of length is acting as an antenna of some sort. So yeah, for higher frequency use, the attachment of this probe is very specific, but for most, you know, AC measurements, if you're going to be measuring in the kilohertz, most people wouldn't be measuring, you know, any type of an AC frequency, you know, much beyond the audio level. If you're into RF and you want to use this as an RF probe, that's absolutely fine, but it does take a little bit of knowledge to understand that, you know, lead length and, you know, the way that things are connected will really impact the reading. So, and of course, you know, again, you know, a piece of lead length like this will act as an inductor at higher frequencies. So things like that need to be known. Again, I will go over more of this stuff in the future and how to attach these things. So RF gets a little bit tricky. Audio is a little easier to work with. So that's just the way it is. So as I've said many times before, if you're into the RF world, once you understand the way the RF world works, it'll make understanding the way audio works seem so much easier. So it's kind of walks up the ladder, I guess you could say, in frequencies. The first thing I'm going to do before I start the alignment is set the filament voltage of the tube in the probe. So that's a very important thing to check. It's very easy to do. So this pink wire here, that runs to the tube. We'll put our AC voltmeter on there, and I can just touch the chassis and get an idea. That's 7 volts, so that's pretty high. It's supposed to be at 6.3. So the adjustment point is right there. This one right here. Looks like somebody's marked a line on there. It doesn't look to be too accurate. So what I'll do is I will put my screwdriver in that adjustment point, just like so. And I will bring this down 6.3. I'll bring it just a touch over 6.3, just to deal with line variation. So the line variation here is, this line is actually pretty high at the bench. So a normal line would probably be right at 6.3. So that's close enough. And that will definitely save the filament in that little tube. So, probe filament voltage adjusted. The very first thing to do in this calibration procedure is set the 1 volt scale. So that's the DC cal setting. That should be done first. So I have it in positive volts here. I have the leads shorted on the test fixture here, or the calibration fixture. So I'll zero this up. That's pretty close to 0 to my eyes. I'm looking at this straight on. It might look a little bit off to you because you're on a bit of an angle. It's kind of hard to get everything all in here. So I'll attach this to the fixture, let things settle off for just a moment, and I will press positive 1 volt. And that is so incredibly close, just from the bench, it's almost not worth even touching. So I'll shut this off. Check it again. So I'll take these 2 leads and short them. That's pretty close. I'll attach this back up here again. And try it one more time. Yes, that's right on the 1. So that's just from the bench calibration. It's still spot on. So I don't need to calibrate that scale, which is nice, and that allows me to calibrate everything else after this point. The next step in the alignment is to do the 1 volt AC calibration. That is this variable resistor right here. So it's right beside that filter capacitor. That's the one that needs to be adjusted. And it's pretty much the same procedure for all the rest of the scales. So I'll just show you how I do this one, and all the rest of them are, again, pretty much the same thing. So I'll click it onto AC here. And what I need to do now is zero the meter again. So I'll take the AC probe, hopefully you can see this, and I'm just going to short that there. And now I just want to adjust the AC. I don't want to touch the zero behind, I just want to touch the AC zero. So move that around. Very touchy control. Probably because I'm moving the probe too. So there it is. That's right on the zero mark, at least to my eye anyways, at this angle. So what I'll do now is I'll put my little jumper clip on this. And what I'll do is I'll switch this to AC. And then I will shut this off. So it's at 60 cycles right now at 1 volt. So I will attach this here like this, and I'll just set the probe down very gently. And I'll turn it on. See where we are. Well, that's very close. So now what I need to do is move that up to the 1. So hopefully I can do this from this angle. Right about there. Right on the number 1 to my eye. Yep, right on the number 1. So what I'll do is I will shut this off. There. And I will ground the probe out here again. Or hook the common to the center anyways. And that's right on 0. So that scale is now calibrated, and it's the same thing. I just go up to 3, set this to 3 volts, adjust it for 3, all the way up to 300 volts, and adjust the 300 volt scale on the back. So that's it. So I'll get going with that and get that all calibrated up, and I'll adjust the ohms here as well. So it's not really an adjustment. It's basically just to make the two scales somewhat align at infinity. I'll explain that when I get to that point. I should mention, to lessen alignment confusion, the 1 volt AC and the 3 volt AC scales are the red numbers, and you have to align them to those red numbers. Now the 1 volt upper scale and the 1 volt scale here, which is the AC scale, they align with each other, so you can pretty much just use the needle, and the needle will rest on top of both of those markers. But you'll see how the 3 volt stops down here. So I'll give you an example. I'll turn on the alignment fixture here. And you can see how it's stopping right there on the number 3. So it doesn't go right to the end. And that's very important for your alignment accuracy. I'm over on the 300 volt scale now, and the thing just aligns up so incredibly nice. So I'll give you an example here. So the calibration fixture is set to 300 volts. I'll turn that on. It's at 60 cycles, again, as you can see. You'll see it'll go right over to the 3 here. That noise is just warning you that it's putting out high voltage. Right on the number 3. So I'll turn that off. Go down to 200. So it should be right on the 2 there. In fact, you know what? I'll zoom in just a little more. You can really see what's going on. Focus off of that. So there we go. Alright, so I'm at 200 volts now, so it should be right at that 2 on the second scale down. So here we go. Look at that. Right on the number 2. 200 volts, I'll turn that off. And I'll go down to 100 volts. And we'll try it again. Should be right there. Look at that, right on top of the number 1. So, very pleased with this so far. Again, this is just a preliminary alignment. As soon as I put this in the case and let it warm up for about 45 minutes, I'll go through it and do another alignment on this completely all over again, just to make sure that everything is spot on. So the reason I'm doing this open is so that you can see this. There's also something else that I will show you in here. There's a bunch of different versions of the 410B, and they have different cards on the side. And they don't mark some of the variable resistors, and it's kind of hard to find the information on that. So I'll share that information with you here on the other bench. Here's some information that may benefit you if you have an HP 410B, the same version I do. You may have a rough time finding what these VRs do and their identification. So this upper one right here is the 30 volt AC adjust. This one on the bottom is the 300 volt AC adjust. And then the one on the back side, which is right there, you can see that one that's right there. That one is the 100 volt AC adjust. So right down there. So that's a little bit of information that sometimes is a little bit hard to find, especially with this version right here. Here's how we make the infinity align on both the R times 10 and R times 1 scale. So of course we're in the ohms because we're measuring resistance. So what I want to do is I want to adjust the infinity here to the last line just before the infinity symbol. I'll show you this here. So right about there. And what I'll do is I'll short the test leads here to make sure that it's zeroed correctly. And it is. Very, very close. On the bottom scale there. Could get touched up just a bit. Right there. It's good. So I'll recheck that. And yeah, it's pretty much on infinity. I'm being a little bit picky here. Here we go. One more check of 0. Yeah, no problems. Okay. Again, there's temperature variation while I'm doing this here. It's not in its case, so things will move around a little bit. So now what I want to do, now that I've done that, I've set this on infinity, that last line there. When I click down to R times 1, it should stay at that same spot. And if it doesn't, I need to make an adjustment on the back. And as you can see, it moves. So there's a variable resistor right beside the ballast tube, and that one will allow me to adjust this one and bring that scale back up. So what I'll do is I'll just put this in that variable resistor, like so, and move that up to infinity. Right about there. Very close. And there we go. And as you can see, now it aligns on every single scale. Here's an example of the usefulness of a vacuum tube voltmeter when taking a look at very sensitive circuitry that doesn't have a whole lot of current behind it. And this is really an example of not loading the device under test. Now, I recently did a video about this on Patreon, and I'll share a clip of that video here showing you how a normal DMM, digital multimeter, or benchtop meter will drag the voltage down in a very sensitive circuit, whereas a vacuum tube voltmeter like this will remain invisible. Now, the meter that you're going to see, the VTVM that you will see in that video, looks a little bit different than this, but it's pretty much the same design. It's just the military version of this particular meter. The reason I didn't show this meter in the video is, well, I didn't have it restored at that point. So let's take a look at that clip, and I'll give you an example. And you can actually see how one of these DMMs or multimeters, any type of multimeter, will drag the voltage right down, whereas this will stay virtually invisible to the device under test. Here's a good example of circuit loading. Now, a lot of the, I guess you could say the newer techs, seem to think that these meters are just as good as vacuum tube voltmeters, right? Well, in some cases they may be, and in other cases they're not. So these two 1 megohm resistors right here are these two 1 megohm resistors right here, okay? So we're going to be taking a look at the actual AGC line. So what the AGC line here does is we have a path that runs all the way over here, and then it runs up through the coils. We have a DC path that makes it onto the control grid of the actual IF section. So you can see there's if you look at the control grid here, right, you can see it goes through the IF transformer, and then we have a resistor here, and it runs down to the AGC line right here, right? So we have a capacitor on there, all right, to basically keep RF off and to give it a bit of a time constant. That's what the capacitors do on the AGC line. So the time constant of the AGC line is basically how quickly it responds to a strong signal. All right. Now, being AM, it's like you tune into it, and usually it is strong. When you have skip conditions, or I guess you could call it atmospheric conditions, depending on the way you want to look at it. If it's a fast-moving condition, sometimes you get a bit of overloading on a slower circuit, but this seems to be just a beautiful balance. It doesn't seem to ever do that. This is the eye tube. Okay, here's a trick. All right. You can watch the eye tube on here, and I'm going to touch the automatic gain control line with the meter here. Okay, so I'm going to touch this resistor right here. I'm just going to touch the lead on it. And I'm going to zoom in on this so I can give you a better view of just what's going on. And maybe I can move the focus onto the meter a little bit here. Nah, I can't get them both at this distance. Okay, so you're going to have to deal with this being backed out just a little bit. First of all, actually, here we go. First of all, what I'll do is I'll touch the AGC line with the probe and watch the eye tube. Okay, so watch what happens to the eye tube here. So I'll tell you when I'm touching this. Get this down into here. Okay, so here we go. See what happened? So I'll remove the probe. I'll touch it again. You see that? See how it's moving in when I'm touching my DMM's probe to it? Let's see if we can get a little bit better focus on that. Okay, so here we go. That's a little better. So here we go. I'm going to touch it right now. Now I'm going to remove it. See how it's affecting the shadow angle when I'm touching my probe there? You know why it's doing that? Is because this fancy dancy DMM that you see here on the bench, that's supposed to, be a relatively high input resistance or impedance, is loading the circuit. Now, another way to tell that is when you touch your probe to a circuit and the numbers slowly count down. Okay, so you'll find that it'll slowly count down, and that's that capacitor on the AGC line. That's the probe and the loading of this meter, which is a relatively high impedance or high resistance meter. Let's move the focus there. Is loading it down. This is like this relatively high resistance or impedance meter is pulling the circuitry down. I can even pull it down with a brand new wax capacitor I have. If I put a brand new, out of the box, leads on it and everything, wax capacitor, put that on there, you can actually watch the eye tube move. So I may display that too. Okay, so here we go. Now watch what happens to the meter. I'm going to touch it to the terminal now. See it counting down? Now if I remove it, and I'll touch it again. See how we started at about 4 volts? Okay, so here I'll tap it again really quickly, and you'll probably see that first digit go to 4. No, that one didn't catch it that time. Let's see if I can maybe make this a little bit quicker by bringing it up a range here. So a couple of ranges. So here we go. Yeah, see how it tapped 4 there? And now it's basically almost pulling it down to 3.3 volts, probably 3.2 something. It's sticking at 3.3. Okay, it went to 3.29 something or other. Okay, and I'll remove the probe again. You might even be able to see the blurry shadow angle move as I do this as well. So here we go. Now that's because this meter is loading the circuit. Now you're thinking to yourself, well, maybe it's just this meter, right? Maybe it's just this Agilent. All right, so what I'll do here is I'll just grab this one here. Okay, so there's another one. This is the one with the remote head on it, right here. All right, so let's see what I'll do. I'll just leave that on. Just unplug this. Plug this into this meter here. Okay, so here we go. Let's try this one. Oh, there we go. All right, so take the probe off. See if I can even get that in there. Right at the screen, you see my probe right down here, so I'll poke this right now. That's 4 volts, and we're dragging it down to 3.3, so we're giving ourselves a false reading because the meter is loading the circuit. Let's try this VTVM to look at the AGC circuit. So I'm on the 10 volt scale, which is the upper scale, so 1 is 10, and this is 8, 6, and 4 volts, and 2, and down, right down to 0 there. All right, so it might look a little bit off because it's on a bit of an angle here. And this meter really doesn't like sitting on its backside. It likes to sit straight up, but it'll do a pretty good job of displaying what we need to see here. So keep an eye on the tube and the meter, and I'll touch that same point right now. If I can get it in there, there we go. All right, so I'll remove the probe, ground this out, and I should probably zero that up a little bit better. Even on my end here, it's a little bit above the old 0 mark there. Okay. Let's try that again. Here we go. Look at that. Right where it's supposed to be. 4.1 volts. That second little bar that you see right up there is 4.2 volts. Okay. All right. Here we go. Look at that. No movement of the eye, reading exactly what it's supposed to. This is actually a shielded piece of cable right up to the probe, because this is a very special type of voltmeter. Now I'm going to be doing the restoration on the Hewlett-Packard version of this voltmeter here very shortly, and I'm even going to upgrade a bunch of little things inside there. So I'll just show you the AC probe here. These things are good into the gigahertz. So this is a really fancy looking probe, and it's nice and hot because there's a vacuum tube inside here. And a very special meter. Again, you know, great for looking at RF voltage and things like that. I'll just put this on the bench here. You gotta be very careful with these things. Somebody's dropped this and already busted this before I had it, so I had to fix it. You can see the hairline crack here. And I had to make the probe because this was missing. And so this is basically just a long screw that I've sharpened on the end, and I've put this here to protect it. So the cap, you can remove the cap too, and all that kind of stuff. So the probe on the Hewlett-Packard version I like a little bit better because it's you know, a little bit smaller than this. This is a really big probe for looking at RF voltages with, right? Now keep in mind that you know, what you're going to be reading, depending on the frequency, is going to be, you know, largely dependent on the size of the tip as well. Just because, you know, when you're looking at gigahertz frequencies, even UHF frequencies, the length of this is going to skew your results because this looks like inductance. Now I'm doing the component, this series on components here on Patreon, and we're going to take a look at inductors and things like that, and I'll explain a little bit more about that. So when we start looking at different types of components in that series. So I wanted to share this with you now because this is very important, and I have this opportunity again because this radio is out, and this is such a prime example of a you know, very high resistance or high impedance circuit, depending on which point you look at it. It's a very, very good example. If you enjoyed that video clip, definitely check out my Patreon page. There's over 100 videos up there right now, and I'm sharing many of my personal designs and inventions. So there's lots of great technical information there if you want to become a great electronics technician or a great electronics engineer. Definitely check it out. You'll enjoy it. If you're enjoying my videos, you can let me know by giving me a big thumbs up and hang around. There'll be more videos like this coming in the near future. We'll be taking a look at vacuum tube and solid state electronic devices alike. So there'll be a lot of repairs, restorations, circuitry design, all sorts of electronic related content on this channel. So if you haven't subscribed, now would be a good time to do that as well. If you're interested in taking your electronics knowledge to the next level and learning electronics in a very different and effective way and gaining access to many of my personal electronic inventions and designs, some of which you've seen in this video, you're definitely going to want to check out my ongoing electronics course on Patreon. I'll put the link just below the video's description under the Show More tab, and I'll pin the link at the top of the comments section. So if you click on the link, it'll take you right there. All right, until next time, take care. Bye for now.